In this example, we are going to talk about a few examples of these resistive circuits. So let's look at the first example. In this example, it has an independent voltage source and it has a dependent voltage source and its voltage control voltage source. So the voltage of this dependent voltage source is 4Vx. Okay, so how can we solve this problem? Please remember, so there's so far we talk about KVL. It means in any loops in a circuit, the summation of voltage is zero. And we talk about KCL. KCL means the net current of a node is zero. And we talk about voltage division rule. We talk about voltage division rule. And so if resistors they are in series, then the voltage across each resistor is just a fraction of voltage source, right? And we have current division rule. So we have a formula to calculate the current. If resistors they are in parallel, then you can always resort to that formula to divide the current. And we also have Ohm's law. Ohm's law. And pretty much it. There are simple rules to calculate the current. Of course, later on we will introduce a more complex techniques such as nodal voltage analysis and mesh current analysis. But for simple circuit, these 1, 2, 3, 4, 5 rules should be enough to solve the problem. So we go back to this example. How can we solve it? By observation. So let's try if we look at this loop. So so in this loop, this component, we have voltage of this component, and then the voltage across this 0.5 ohm resistor is Vx, and we need the voltage across this 4 ohm resistor. But here, can we know the voltage difference between this 4 ohm resistor? Yes, we can, right? Because these two elements, they are in parallel, which means they share the same top node and bottom node. So the voltage here across 4 ohm resistor should be the same as the voltage difference of this dependent voltage source, right? So within this, so we have positive, we have negative 4Vx. So by KVL of this small loop, starting from bottom left corner, we have minus 10 plus Vx plus 4Vx equals 0. And then we have 5Vx equals to 10. Then Vx equals 2 volts. So we find Vx. Another point of view, another point of view, because here for this 4 ohm resistor, The problem doesn't specify the voltage across this, so instead we look at this outer loop because luckily on this outer loop, all the voltage across the components, it is defined or given as a variable. So from here, bottom left corner, minus 10, here, minus 10, plus Vx, plus Vx, plus 4Vx equals 0, same equation. Okay, so no matter no matter how, so as long as it is in the circuit, these rules they all need to be satisfied. Okay, so we find Vx. That's a good start because we solve one unknown variables, and then it asks us to solve Iy. So how? Iy is a current, and current flowing out from this node, which means we need to calculate all the current, the net current of this node. Okay, so if we know Vs is 2 volts, and we define the problem gives the polarities, which means we know the current. Let's say if this is I1, I1 needs to be I1 need to flow from positive terminal to negative terminal of a resistor. So we can calculate I1. Sorry, calculate I1 equals 2 divided by 0.5, which is 4 ampere. Okay, is 2V. And can we calculate this I2? Yes, we can. But do you know why I define the direction of I2 is going down? Because I know these two are in parallel. So we have positive, negative for Vx. So it should be 4 times 2, it should be 8 volts, right? And the polarities, it follows the polarities of this dependent voltage source. So we can calculate I2. So I2 equals 4 Vx divided by 4, which is 4 times Vx is 2 divided by 4, which is 2 ampere. Okay, we find I1 and I2. Then we have this, suppose this is node 1. So KCL at node 1. KCL at node 1, which is we have net current I1 plus current flowing into the node, current flowing into the node just I1 equals current flowing out from that node, which is I2 plus Iy. So we have I1 equals 4 equals 2 plus Iy. So the value of Iy is 2 ampere. Okay, and then we got the answer. So when you are given a circuit and you need to calculate the current and voltage within the circuit, the first thing is you always need to think of these rules first. Okay, because you can always observe there's some uh, there are some hint for you to calculate. Okay, all right. Let's look at the next problem. Okay, here it is a current, independent current source. This is dependent current source. Solve for IS. What type of sources are present in the circuit? Okay, so it has an independent current source and it has a dependent current controlled current source. So by observation, what what do we have? Um, Here it says, it gives us a hint. It says this is 15 volts. If it's an error and says it's 15 volts, it means this is positive. This is negative. The direction of error is positive. Okay, and we can observe a few things. For example, look at node 1. Well, we can apply KVL at node 1, or KCL at node 1. Why not KVL? Why not KVL? Because we don't know the voltage difference. Wait a minute. Sorry. Let's go back to. Give me a minute. Let me. Let's go back to our slides. Where's our slides? All right, good. Why not KVL? Because we don't know the voltage different. We don't know the voltage across this current source, and we don't know the voltage across this dependent current source. So it's too many unknowns, and then we don't want to increase the number of unknown variables. But so no KVL for this. However, if you observe at node 1, so the current flowing into node 1 should be Is, right? Flowing into node 1 plus Ix and equals Ix over 3. Okay, we got an equation here, and we do not use any extra variables. These variables, Is and Ix, they are all given by the problem. Okay, but we have two unknown variables, and it looks like we need to try to solve one first. And then and then I noticed this 15 volts. And so this is positive. The direction of error is positive and negative. And this is 5 ohm resistor. So if you are given the voltage difference of a resistor and you are given resistance of this resistor, then by using Ohm's law, and then we know the current, for example, this is I1. The current I1 always flows from the high potential energy to low potential energy, which means it flows from positive to negative terminal. So I1, so we leave this because they're two unknowns, but we can solve I1 first. I1 is 15 divided by 5, which is 3 ampere. And if we look at this node, because I know Ix equals minus I1, right? Because if we apply KCL here, this is node 2. But if you are good enough, you can immediately observe that Ix equals minus I1. But if you cannot, then we apply KCL at node 2. Then the net current of a node is 0. So Ix plus I1 equals 0. And so Ix equals minus I1 equals minus 3 ampere. And since from equation 1, this is equation star. How about equation star? So we solve one variables Ix for this equation star. So from equation star, we have Is equals minus Ix plus Oh, sorry. Let me try to recover. Okay. Minus ix plus ix divided by 3 equals minus 2 over 3 ix. And then we put this ix into this is minus 2 over 3. This is minus 3 and it's 2 ampere. So is 2 ampere. See, it's not very hard. There are simple problems. Hey, supposedly you should be familiar with these rules, and then we go to more complex diagrams. So next, this is a more complex circuit diagram, and then we need to use so here, although we can still solve it by using the previous rules that we introduced, but we now need to apply a more advanced technique. So here, solve for the node voltages, show and determine the value of the current Ix. So you need to calculate Ix, but this problem already specified that you need to solve node voltages. So by looking at this circuit, um, a ground has been given to you. So this is 0 volt. Usually, we define the ground, we connect the ground to the negative terminal of a voltage source. But in this problem, it doesn't have a voltage source. So we can define the ground at any nodes. But here, we just put it here randomly. Okay. And so we have, because there's no voltage source, we have V1, V2, and V3. It has 1, 2, 3, 4 nodes and 3 variables. Because we do not have any voltage source, so we cannot, so these nodes are, the voltage of these nodes are unknown. And then, so this is node 1, this is node 2, this is node 3. So KCL at node 1. Get KCL at node 1. Okay. Uh, and I mean KCL at node 1. Yeah, we use nodal voltage analysis, but we apply KCL because we need to convert the current to the function of voltage variables. Okay, so for here, we assume that at node 1, we assume the current direction is this. So if the current direction is flowing into node 1, and then for this current, and I mean, for this current, it should be 0 minus V1. So for that current is 0 minus V1 divided by 10. And then we look at this current plus V2 divided by V1 divided by 5 minus V1 divided by 5. And then, although it says Ix, but I intentionally assume that this is the current flowing into V1. So I can use V3 minus V1 divided by 20. V3 minus V1 divided by 20 equals 0. Because previously we explained that the direction of the current, the assumption of this direction of the current doesn't matter. But once you define the direction of the current, then the difference of voltage must has a direction. All right, so this is for V node 1. And then node 2, for node 2, and then so we erase this. And then, so if we look at this, if we assume there is current in this direction flowing into node 2, then we have V1 minus V2, V1 minus V2 divided by 5 plus 10 ampere plus, I assume that always flow into the node. So we have V3 minus V2 divided by 10 equals 0. And so if we focus on node 3, then we erase this. Right now we assume current. So we assume current from here is V2 minus V3 divided by 10. So here is 0 minus V3 plus 0 minus V3 divided by 5. And then here, this is V1 minus V3 plus V1 minus V3 divided by 20 equals 0. So we have 3 unknowns, 3 equations, and let me double check if they are correct. And yes, they are correct. V1 minus V2 plus 10. Okay. All right. So you can, by rearrange this, you are able to find out 3 equations, 0.35 V1 minus 0.2 V2 minus 0.05 V3 equals 0, and minus 0.2 V1 plus 0.30 V2 minus 0.1 V3 equals 10, and you have 0.05 V1 minus 0.1 V2 plus 0.35 V3 equals 0. Um, of course, you can solve it. And if you have these calculators, and if you have these engineering calculators, you can write this into a matrix, minus 0.2, 0.05, but I don't have one, so I may have to solve it one by one, but if you have one, then 0.05 minus 0.5, and this is 0.35, and then we have V1, V2, V3 equals 0, 10, 0. So it can be written as matrix A times V equals, so this is a matrix, equals B, so V equals B. So you can calculate the inverse. So we calculate the inverse of A, so times the inverse of A, B. So this become an unit matrix. So which means V is V1, V2, V3 equals A minus 1, the inverse matrix of A times B. Okay, so if you have engineering calculators, and then you can input this matrix, if it can perform matrix manipulation, and so this is matrix A, and this is matrix B, then the inverse of matrix A times the matrix B will be your answer. And so here, does it say V1, V2, V3? Yes. So V1, I write it here. I'm not going to I'm not going to solve it. V1 is, you can double check. V1 is 45.5. V2 is 72.7. V3 is 27.3 volts. Volts. Are they correct? Let's put it here. How about let's put it here? So I'll pull out my calculators. So minus, it is, yeah, this is a way to double check. So we have minus 0.2 times 45.5 plus 0.3 times 72.7 minus 0.1 times 27.3 equals 9.98. It should be close enough. So this answer is correct. Okay, so please always double check your answer. All right, and then we go to next problem. In this problem, it's mesh current analysis. So mesh current analysis, so we define meshes in this diagram. Mesh is the smallest loop. So we have 3 meshes, and this 2.14. Okay, we look at mesh 1. So we applied KVL at each mesh. So for mesh 1, starting from bottom left corner, and this is I1 is running clockwise. And then so here, the voltage across this 20 ohm resistor, because we focus on mesh 1, so it should be 20 times I1 minus I3. So because we are applying Ohm's law, and the voltage across a resistor equals its resistance times current, and because we assume mesh current I1, and we also assume mesh current I3, this resistor is shared by I1 and I3, and they are in opposite direction, so the voltage needs to be 20 times I1 minus I3. And here we follow the direction of I1, which means I1 comes into the positive terminal of a resistor, because a resistor always consumes energy. But here, the voltage here is 10 times I1 minus I2, because I2 is in opposite direction of I1. So starting from the bottom left corner, so I have minus 70 plus 20 I1 minus I3 plus 10 I1 minus I2 equals 0. Okay, and then we focus on mesh 2. And then I want to use different color. So we focus on mesh 2. So here we just focus on this mesh. So here is positive negative. So the voltage across this is 10 times, but right now we need to calculate from the point of I2. So it should be I2 minus I1. And this is positive negative. This is 12. I2 minus I3. And this is positive 42. So we have, starting from bottom left corner, we have plus, I have plus 10 I2 minus I1. We have plus 12 I2 minus I3. and we have positive 42 equals 0. Okay, and this is we apply KVL from the perspective of I2. And right now we look at mesh 3. Mesh 3, and I want to use a different color. Oh, my bad. Different color is this, how about green? So right now we need to, from the perspective of I3, so which means this is positive, negative, and it's 20 I3 minus I1. Okay, and here is this is positive, negative, this is 14 I3, and this is positive, negative, this is 12 I3 minus I2. Okay, so we apply KVL starting from bottom left corner. So we have plus 14 I3, and then plus 12 I3 minus I2, and then plus 20 I3 minus I1 equals 0. So let me double check if these equations are correct. Let me double check. And 70, 20 I1 minus I3, 10 I1 minus I2, and then this is 10 I2 minus I1, plus 12 I2 minus I3, plus 42, and it's 20 I3 minus I1, and then 12 I3 minus I2, plus 14 I3. So this is correct. And then you just need to solve the problems on your own. So I just write it down. 30 I1 minus 10 I2 and minus 20 I3 equals 70. And we have minus 10 I1 plus 22 I2 minus 12 I3 equals minus 42. All right, and then we have one thing left. One is minus 20 I1 minus 12 I2 plus 46 I3 equals 0. So it should be correct. And for so I1, so when you solve it, I1 equals to 4 ampere, I2 equals 1 ampere, and I3 equals 2 ampere, which is the answer. Oh, this is the this is the answer. Okay, so this is mesh current analysis. We'll apply 8 kVL and try to calculate the summation of the voltage across each element in a loop, in a mesh, and then we assume mesh current. So the voltage drop of resistor can be represented by the resistance times the mesh current. And if the resistor is shared by two meshes, then you need to subtract um, the other mesh current because the mesh currents they are in opposite direction. Right, that's what you need to memorize. Okay, let's look at next problem. Hmm. Um, so for the currents in the circuit of this speaker, which contains a voltage control current source common to the two meshes, and because it asks us to apply mesh current analysis, right? So we just and it's giving us mesh currents. So just follow what is given by the problem. And then we look at the first mesh, and then we can immediately define that, wow, we have this positive negative 4 times I1. And then we have a problem here. If you look at the first mesh, huh, we have we don't know the voltage difference of this dependent current source. So and there's no way to get away from it. And then what we can do here is we look at the, so there's no way to avoid this. The only way to avoid this is we look at this big mesh. Okay, if we look at this big mesh, then the voltage across this 4 ohm resistor is 4 times I1. And the voltage difference of this 6 ohm resistor, because the direction of current is this direction, so it's 6 times I2. All right, and this is Vx. Uh, Vx can be, because we don't want more variables. So this is Vx equals positive negative 2I2, right? So Vx, we know Vx is actually 2 times I2, 2 times mesh current I2. So we can get rid of one variable, right? The reason that I write this. So if you look at this big loop, big mesh, apply KVL. So KVL at big mesh. So starting from bottom left corner, we have minus 20 plus 4I1, and so we keep going, plus, this is plus 6I2, and then plus 2I2 equals 0, right? So we have an equation of I1, I2, but we need another equation. But what can we do? Um, by the way, A here should be what? 0.25. Okay, A equals 0.25. This should be given. We have one equation, but two unknown variables. We need another one. So another one we can look at here. Because in this dependent current source, the current is from this direction. This direction is the same as I2, but in opposite of I1. And the value of the current is 0.25 A times Vx. So we know A times Vx, because it's at the same direction of I2, it should be I2 minus I1. And then from here, we know we put in 0.25 as to replace A, and then we know Vx equals 2 times I2. So we have 0.25, we have 2 times I2 equals I2 minus I1. So we have this 0.5 I2 equals I2 minus I1. So we have this I1 equals 0.5 I2, which means I2 is 2 I1. Okay, so right? I2 is 2I1, then we can plug in into this equation and okay, so I2 is 2I1, so solve this equation, we have minus 20 plus 4I1 plus 6, this is 2I1 plus, oh, this should be 8, right? So we just write, combine them, we have 8, I2 is 2I1 equals 0, then I1 equals 20 I1 equals 20, I1 equals 1 ampere. Okay, and once we have I1, so I2 equals 2 I1, so I2 is 2 times 1 is 2 ampere. So we solve I1 and I2 successfully. So the tips to calculate circuit diagram is first you need to observe. Please always observe the problems and try to think if you can apply basic rules. And if basic rule cannot be used or is too complex, then we can consider nodal voltage analysis or mesh current analysis. Okay, let's look at one more problem. Okay, um, okay. So use mesh currents to solve for the value of Vx. They want to solve Vx. In the circuit of this A, and this rather complex circuit has been contrived mainly to illustrate the steps listed above. So, okay, so here it looks, for A, it looks very complex. And then we can try to, because these three resistors they are in parallel, so we can calculate the equivalent circuit. Equivalent resistance is 5. So how can we calculate Req? You should be able to know that this is 1 over 15 plus 1 over 15. Oh, these are three. They have the same resistance. So the equivalent circuit for them is just 15 divided by 3 is 5 ohm. 5 ohm. Okay. And so for here, it has I1, I2, I3, three mesh currents, and it has two Vx, and Vx is the voltage across this 10 ohm. When I look at this, I can immediately replace Vx by what you should know. This is positive, negative directions of I3. So the voltage here, it should be 10 I3. So I immediately know that Vx equals to 10 I3. Okay, so I can replace Vx by 10 I3. So I keep 3 unknown variables, not 4. So we just need to list 3 equations. Same thing here. We define the polarities of these components. Uh, oh, here we don't know the voltage across this. We don't know the voltage across this current source, so it has a problem. So we kind of avoid it. We can only resort to this loop. Okay, so this is positive, positive, negative, 5I1, and this is positive, negative, 6I1 minus I3 because it is shared by I1, I3, and this is negative, positive 2Vx, but Vx is 10 times I3. So this is 2Vx equals 20 I3. And this is positive, negative 8 I2. Okay, so we can, once in this big mesh, we define the voltage across each element, and then we can perform KVL. So KVL for the big mesh. So we have positive 5I1, we have positive 6I1 minus I3, we have this minus 20 I3, and then we have this plus 8 I2 equals 0. Okay, and then we can define, we can define the mesh here. So, but right now we need to define the voltage based on the direction of I3. So this is positive, negative 6 I3 minus I1. Okay, so from here, bottom left corner, we have plus 10 I3. So KVL button. Okay, KVL for the for mesh 3. Then we can write positive 10 I3, and this is this, you hit plus first, so we have plus 20 I3 because we have converted 2Vx to 20 I3, and then plus 6 I3 minus I1 equals 0. Okay, double check. So, yeah, should be correct. Okay, and right. Okay, and then but we have two equations, but we have three unknown variables. What can we do? We need to have one more equation so we can observe this. This is 22 ampere is the current source. It's in the same, it's at the same direction as I2. So we can say 22 is I2 minus I1 because it is shared by I1 and I2. It's in the same direction of I2, but in the opposite direction of I1. So 22 equals I2 minus I1. And the answer should be, you can calculate it on your own, but the answer should be I1 equals minus 12 ampere. And I2 is 10 ampere. And I3 is minus 2 ampere. And then let me double check. How about I plug in this to double check. So this is 5. I1 is minus 12, right? This is I1 is 5 times minus 12 plus 6. I1 minus 12 minus 2. Okay. And then minus 20 times minus 2 plus 8 times 10 equals, okay, let me run the calculators. So we have 5 times minus 12 and plus 6 times minus 10 plus 40. and plus 80 equals 0. So yeah, it is correct. It is correct. So this is the answer. Okay. Um, so for the other problems, okay, this is our last problem. So we talk about this example problem to help you to review these rules and including nodal voltage analysis and mesh current analysis. And hopefully, if you still do not understand, please work on the homework. Okay, this is what we teach for this offline video.